Alright, so we continue with with the topic of analysis of tensor fields. And again, so we work in the Cartesian coordinate system so far, and so we define a few important differential operators. Now, some of these operators, such as, for example, the gradient of a scalar, that is was already defined and used in different courses. Now but application of this similar operator to higher order tensors, for example, for vectors, that is, and second order tensor, that's already might be something that we need to provide more details here. Now, for so we defined this grad f psi or phi as or phi as her in the following way. So phi is still a scalar, but it's spatial. It's some function that can it depends on the so it basically represents a field, and its value of the scalar may depend on the position in the field. And so the way to describe it is the change of that function from point to point is to describe the gradient of that, which is basically we're taking the partial derivative with respect to the position vector x, right? And and the components of such, so the result is of course a vector, as you can see in this notation, and the components of that vector are derivative of this scalar function psi with respect to x, corresponding xi in our coordinate system. Now this is for the scalar function. So again, you can think about something that you encountered before. It can be the scalar function can be, for example, a pressure in fluid mechanics, and the gradient of pressure will indicate the direction of the of changing of that scalar, and can be connected to the creation of driving forces for the equations of motions that you need to solve. Now we also can have a situation when we have a different field, for example, a field of vector field, depending on the location. Again, so that connecting it to our neighboring discipline of fluid mechanics, so that could be, for example, a distribution of velocity in, let's say, a pipe or some other configuration, and so you would want to characterize such as changes in the velocity, spatially, by also calculating the gradient, right? Now, the result of such operation of a gradient of a vector, let's say A, in this context, would produce us a higher order tensor. So you can note that when we took a scalar, just a grad of a scalar, so we increased the the order of the tensor, so we produced a vector, first order tensor. Like now we take this gradient differential operator over A, and our result will be a second order tensor. So all right, so as you can see, so again, the similarity, so we don't touch, so we basically write in a very similar way as for scalar, and let me write, so if I ignore what I take the derivative of, right, so this operator was just okay, so just this part, and so that exactly replicates it here, right? So when it takes derivative, the components of that will be still EI. So, but because we don't, this is not a scalar here, so we actually have to put here this tensor product. Now again, this is basically our definition of what we mean by that. So, and so now we can expand our vector A and write it as we usually write for vectors in terms of the components and their bases. And so then, right, so this AJ, EJ, this is our representation of a vector. And of course, we're taking the derivative only of the components. So, and so we have this basis dyadic product here of these dyads here, EJ, EI. So you can see that this is, of course, indeed a second order tensor. Now, a different operator can be defined with somewhat similar operation, but in a way importantly different. So we have the gradient operator, but we also have what is called a divergence operator. Aside from the important differences in the physical meaning we take for the examples of that, there are of course mathematical differences in these operators. So divergence operator of a vector will be essentially similar operator but with a dot product, meaning that if we apply divergence on a vector, so we reduce the result of that to a scalar. So it was a first order tensor, that was a vector, we applied divergence operator, differential operation on that, and the result will be a scalar. That is can be seen, of course, here that we have a vector here and have a vector here. So there is a dot product, and dot product is nothing but the that will be a scalar here. So now, so this is important. Then now we can write our vector A in our usual notations here. So AJ, EJ. So this is our vector A components and the basis that was resolved on. All right. So we can recall that there is something that we already introduced. For example, dot product of two basis vectors EJ, EI will produce us, that is our definition was for delta IJ, and so instead of all this EJ, EI, dot product EI, we can write delta IJ, and then delta IJ will act on either J here or I here, making them effectively dummy indexes, and so the result is just like this. So, and of course here we do apply the summation notation, so effectively the divergence of A is nothing but the sum of dA1 dx1 plus dA2 dx2 plus dA3 dx3. So just mentioning that if you forgot how we do that. And one more important notation here. Differential operator that we apply. So we have gradient, divergence, and we have also curl, or sometimes in some alternative literature is a rotor operator. And that again also aside from a different physical meaning depending on to what quantity we apply it and what that will represent. So some may connect it again to fluid mechanics and calculation of vorticity. Here we are so the operator is such that we will produce here the vector product. So we have a vector product here, and as this vector product, the order of multiplication is important. So we define this curl operator in this particular way, and then now we can explicitly write this vector here A as we have done before, and so this again AJ multiplied by EJ, and so we need to couple this EJ with EI through the vector product while we're still taking the derivative of the components of that EJ. and then
similar to what we just done here, we can recall that there is a way for us so that is through the vector multiplication of the basis vectors, we defined, if you remember, the permutation symbol or Levi-Civita symbol epsilon in a certain way. And so we defined in terms of the components of a vector, but basically we also could define it, of course, as the vector product of two vectors through the Levi-Civita that was there. So Kij, Ij, and Ek. So these two, multiplication of these two vectors, vector product, produces the new vector that will look in this manner. And we remember that there is a certain structure for this epsilon Kij when they are not 0 or 1 or -1, representing the vector product. And here there's still things that the components of that the Aj dxi will not change. All right, so another an alternative in some ways way to write these differential operators of tensor fields is to use the so-called Nabla operator, and that's what we are going to do to introduce next. But first, let us complete the list of useful operators on. So we looked into applying these differential operators of the fields like scalars and vectors. Let's complete it by looking into the divergence operator applied to second order tensor. And basically we are following the same structure as we had here in divergence vector A. Just instead of A, we will put here the second order tensor. Okay. All right. So so divergence A will be written in that way. And there is one thing. So again, so this is A is a second order tensor, and as a result of divergence operator, we reduce the order of the result. Will be a reduction in the order of the tensor, so it will be first order tensor, it will be a vector. Now, when we wrote divergence of vectors, we actually had to put dot here. We actually had to put dot here before, indicating that the correct way to calculate the product between two vectors. Now, as you remember, our agreement was that if we have a tensor that is multiplied by a vector, or tensor acts on a vector, so we don't write the dot, but we actually mean that there is a dot, right? So the result of multiplication of a second order tensor with the vector, that will be a vector. Now, and such way, again, I just mentioned that one more time, so we can ignore, we can save and not to on writing dot here. It's again just a notation for this. Now, what do we do here? So we we write this A second order tensor in our usual way. We can expand it and write in terms of the components. So let's say that will be DAMN. So these are components, and the basis for dyadic product here of the basis vectors will be EM. So this is all our second order tensor A. And now we take the partial derivative with calculate the components of that. Now, when we write it like this, that means that there is EN EI will produce us will produce us the dot product, right? And so that will be Kronecker delta, and then will be delta IN. And so I can, for example, choose that that will work. The delta IN will apply to this index I, so I can replace that I with N. And so the result will be, so the the components will be DAMN with respect to DXN, right? And so the one vector component that survives here, the actual vector, is EM, right? And the corresponding component, so this is a free index M here, and N and here are dummy indexes. And now you can see, so this is, as promised, this is indeed is a vector, and so we can write the components of that as by using the summation notation, Einstein summation notation, and more explicitly can be written just in this relatively simple way, right? So so the first component is this, right? So that's when we put m equal to 1. So m equal to 1, you will have 1 here everywhere in this, and the summation will be 1, 1, 2, 2, 3, 3 repeating. And so for the second component, E2, so instead of m we put 2, and that's where you find this 2 here, here, and here, and the repeating indexes 3, 3, 2, 2, and 1, 1. And the similar manner is also with the component L3. So that's how in general the divergence operator of second order tensor looks like. Now, as already mentioned, we can use a different type of notation. This is a so-called Nabla operator. So when we try to treat our these differential operators as essential products, corresponding product, either vector product or scalar product or tensor product with some sort of vector. And so for that purpose, we define that Nabla as a vector differential operator, right? So this is so which is not a vector by itself. It's let's call it a little bit like a quasi-vector, because you cannot calculate the components of that. So each component of such a vector will depend on what you actually differentiate, on what you apply this quasi-vector, right? So for E1, the component will be the differential operator of the quantity of the field that you try to apply the differential operator. So this again just some notations that we can introduce as an alternative for the previous notation that we just defined, this differential operator. This is important because some literature actually does use it, and this is probably it's a matter of taste who wants to use what, but that may also give you some ways to write your expressions more compactly. Okay, so then let's go ahead and introduce this our gradient, divergence, and rotor or curl operators through this new Nabla or vector-like operator Nabla. Okay, and so and so then for our first one, the gradient of a scalar field, so everything is relatively simple. We just put this Nabla here, and then now you can just you can just basically substitute here this psi, and everything is fine. So that's how that will work for a scalar. Now, to define the gradient of a vector, so we will need to write it a little bit differently, right? So that will be written like that. So we have this gradient grad A. So there is a tensor product, right? So you remember that we need to increase that, to increase the order of the tensor, and so then and another important point here is that we have a transposition here to preserve the right order. So this can be done if we just try to use this operator and multiply with A, then you will see to obtain our original definition of grad A, you do need to add this transposition to obtain the right order, the right indexes in here. So if you still want to use it in the through Nabla. Now, divergence of A. So here the order is not important because essentially, well, that will be nothing but a dot product or scalar product of similar to two vectors that we multiply, and so the order of multiplication there is not that important. Now, and so for curl A or rotor A, so this is the right way to write it properly here with the vector product of these two vectors. Okay, Nabla is again is not a true vector but a vector differential operator. But the analogy is exactly right here. So an important quantity is the last one also is the divergence of a second order tensor. This is which is if we write Nabla, if we use Nabla to write this divergence operator, we do need to transpose the second order as a second order tensor A. Otherwise, we will not exactly produce it in this way. And this is important. I will we'll comment on that one more when we get to the description of our equations that we solve in solid mechanics, which is basically equilibrium equations, for example, here, and that will be the form that we use for equilibrium equation when we require that the divergence of a certain second order tensor, our stress, is zero. And so in some notations, you would write divergence, let's say sigma equal to 0, like that. But in some notation, you will see that in books you will use delta Nabla dot product sigma equal to 0 without the transpose, and that would only be possible to be true if that sigma, your stress, is a symmetric tensor, which in many cases is a correct statement to have stress as a symmetric tensor. However, not all the measures of stress are symmetric, and that's exactly what we will be talking later about the different measures of stress as stress tensors that may not be symmetric, and then need to be very careful to how you write your equilibrium equation. The most of course, so if you write divergence A equal to Nabla dot A transpose, so that will be always correct. It's just again you will see that in many cases the transpose is dropped, and that can be done only for a certain case when A is indeed symmetric. All right, I will so just finish this part by noting that when you encounter this type of notation, you need to be a little bit careful, because this is not standardized very well, and some authors may just use different definitions. So we need to look more closely into how the authors describe the definition. Typically, the authors in the books or papers do provide some indications or some opening statements in what is used. So in our course here, in quite a big body of the literature, people do follow these notations, and will continue with our language as we defined, and this is our agreement for how we will use that. So next, let us continue towards the integration now. So we differentiate things, so our fields. Now let's see how we differentiate these our different quantities, scalars, vectors, and higher order or second order tensors. All right, so we'll start our providing the formula for the integration from analogy of a very simplified one-dimensional case of the integration, and just to remind you and visualize what's going on. But of course, we are going forward to state and at least to write formally the so-called the Divergence Theorem or Gauss-Green theorem for the integration and connecting the surface and volumetric integrations. And so, but let's go back again and one step and look into one-dimensional case. Now, this is very standard integration, right? So we have only one dimension, some function y that depends on x, and so we are interested in integrating such function. Actually, not a function, but its derivative, to make it more simple, as we want to integrate it over this interval. And as you know, indeed, that the result is nothing but, okay, so we just integrate dy dx, so that will be automatically a function y, and then we substitute our values at the boundary of the integration a and b, and typically you just have plus and minus here, but without changing much of the rules, more explicitly put here 1 plus 1 and minus 1, right? So otherwise we just simply would write y at point B minus y at point A, and that is the result of such integration. Okay, very simple, and we would ask probably why would we do that, but here is just to show you the analogy of what's going on here, and so then you can you can connect to the notions of the normal that we will of course are going to use again in our when we write the divergence results for the divergence three-dimensional case, divergence theory. Now so okay, so these are our one-dimensional case. This coordinate x, so there's apparently some function y that changes with x. We don't specify what it is, and so now we have these 2 points, point A and point B, and in this one-dimensional case we can define our vector normal and A that will be negative, will be outside from here, right, and that and B will be positive and in the direction of x. Now, so then we can also say that this normal vector also can be unit vector, so that's what we will require, and that will connect us to these values of +1 and -1 in this one-dimensional case. So basically we can say that these are indeed the values of that normal and B and at point B and end point A. Well, you can start thinking, so right, so the only thing that changed is the direction of that plus and minus, and that because this is still a vector, right? But in 2 and 3-dimensional cases, also the orientation of that could be different, right? So it's at different points. All right, so this is sometimes called Newton-Leibniz formula, and so to put this two fathers of the calculus of today. So these are the phases that will connect us to that, but not without much of the comment on their contribution to the calculus. So the all right. So then let us just extend it to the our case that we are actually interested in, and go to the 3-dimensional case of divergence theorem, and there will be new phases that will appear. There's Gauss and Green that I already mentioned, and of course also Ostrogradsky, right? So these are the people in the periods of time that they need will not really stop and spend too much time on that. If you're interested, there is of course literature behind that. Just one short comment is that typically it's called, of course, Gauss-Green theorem or Gauss theorem, even in the conjunction with the divergence theorem. But so in more international practice, name of the Russian mathematician Ostrogradsky also was added to that. We don't need to know that, just some facts of how the names stick to certain scientific achievements. All right, so we'll stick with divergence theorem for the continuation. And now here, so we're increasing our space now to our usual 3 dimensions. And so we have some volume of some bodies that is enclosed by the area A, right? And so there is some volume inside of this small potato, and the surface here is characterized in each point is characterized by the normal, right? And that obviously can change the direction as we travel on the surface that encloses this volume. Then writing the divergence theorem for the same, some scalar function y of now x in 3 dimensions, right? So that's we can say that this is just will be written like this without really proving it or anything, so because that was already done for you in calculus. So this is your familiar formula, and you see that what is important here is that we connect the integration. So this is a partial derivative here of that function over the volume to the actual integration of the value of that function. I took a derivative here of that function on that value on the surface, taking into account the direction of the surface, and this is the sign of the integration over the surface. And note that here we integrate dv over the volume, and here dA. Again, nothing particularly very new for you, as you have seen this in calculus many times. Now, what is important for us is just to look into that from the perspective how we apply this result for our beloved tensors, right? So we have second order tensors, we have vectors. Okay, scalars are kind of straightforward, written already here. Let's jump to the second order tensors right away. And so the analogous part of that, what we have here on the left hand side, so we can write it also for the tensors. And again, second order tensor, this is not a second order tensor just yet, these are the components. But if we want to make it a second order tensor, we know what to do. So right, so we just when we start writing properly with tensors, we can add this multiplication of the dyadic product of that basis. And all right, so this is how it's written, this derivative. So this you can notice the divergence type of operator here, right? So that's meaning that if we write it explicitly, so we'll have this summation 1 1 2 2 3 3. So there was some sort of that dot product. We called that Nabla. And so more explicitly, so we can write this the analogous formula for the components of the second order tensor in the following way, right? So this is by using this same structure for the right hand side, right? Instead of b, we have this again, the combination that the multiplication of b, ij and j. So this is the integration over the surface. So that takes into account that basically integrates the value, the value of that second order tensor B on the surface as we as we go and multiply it with the orientation on that surface. So that's what we get here. And so essentially we are able to connect the integral of Bij inside with the values that is encircled, enclose this area, and by using the divergence theorem. And so this is again as in terms of components. So what we will do next is just write it formally in terms of tensors, right? So we had that divergence component of Bij. So now we write this divergence B dv. So this is our integral here that we obtain, right? So the integral over the volume inside the volume of the whole potato, that element of the body that we wanted to integrate, and now that can be connected with the value of B on the surface. So we have Bn, and you remember that the Bn product here, we don't write dot here, but that's what we mean. So basically that tensor B acts on vector n and produces a new vector. So the result of this is a vector, and it is integrated over the surface. And here the same, divergence of B is also a vector that is now integrated over the volume. So the result of that is of course a vector. Now analogously we can in a similar manner, right? So we can write this for a scalar. Again, we have that vector operator here, right? So that in this case it will be gradient. So otherwise it would be very hard to connect the different dimensions of the tensors on the left and right hand side. So grad phi is of course a vector, and on the left hand side, so there is still that vector n that appears. So again, whatever is vector or tensor we indicate, we use the bold symbol for that. Now this for scalar, so grad phi, the integration of the whole volume will be a surface integral of phi multiplied by n, and integrating over the area that encloses that. And for vectors, so interestingly, so that is important to note that here we have again back divergence A. So that will be already a scalar, as we remember. So when I apply divergence operator, this is a dot product with Nabla, if you like, and so that will be a scalar, right? That we integrate over in the volume, and so on the surface it also will be scalar, a dot product between that vector value on that surface with n, and so we do this go point by point and integrate all these values over the surface, and that will be the result. So this quite important connections for us, especially the 162, so that we can go from surface to volume and vice versa, quantities, and accounting for the diversions here and bringing back without differential operator. So this important result it will be using in the future. And another important formula, just for completeness, we'll also give it for vectors. It's a so-called Stokes theorem or Stokes formula, when we can connect the integral over the or so-called integral over the contour integral over some curve, and that can be also represented in terms of the integral over the area that is built on that curve. And And so and this is schematics for that. So this is our actual curve, let's say L, and this is represented by these vectors along this curve that one sometimes would call dl, but we will write a dx, a small vector element at each point that points to the direction of this infinitesimal small small vector that defines this orientation. And so if we take some arbitrary vector field A and integrate that over along this curve, so that is the result. This is the integral that we have of this curve. And so the Stokes theorem actually allows us to transform to a surface integral. Again, the surface is built on that curve, and then the result of that will be you'll have curl A, right, where that our Nabla vector operators will appear with multiplied with n dA, and n again is the normal to the surface, so no need to go over the whole surface and do this integration. And basically this is very remarkable. These are very remarkable results. In the case of the divergence theorem is a little bit more frequently used for us, especially in this course, but then this is an amazing way that allows us to establish the relationship between the volume and the surface that enclose that volume, the surface and the curve, and and you can even think a curve and a point. And even again, going back to the very beginning where we started, at quite an amazing result if you start thinking about it as basically the result of the integration of some function that can be as complicated as it can be within the interval a and b. At the end is calculated by just some information that you take from 2 points at the end, and seemingly it's not as important what is the information in between, right? So you just need the function at point A and point B, and you calculate the integral that enclosed all of that. It's an interesting point to think about how it came to that. But again, so just to conclude, so this is the divergence theorem that we wrote for our second order tensor, for scalars and for vectors. That is very important for us, and that concludes this what we wanted to cover with the tensor field in differential and integral operators.